Okay. Hi, everyone. Welcome to our next installment of the molecular modeling machine learning reading group. Today, we're thrilled to have Yeqing Lin from Mohammed AlQuraishi's lab come and tell us about Genie, a diffusion model for protein structure modeling. So Yeqing did his undergrad at the University of Michigan, where I am, but now is at Columbia. So this is a project that he's been working on, and he'll tell us about it now. So thank you.
Hey. Hi everyone. Hi, I'm Yeqing. So I'm a second-year PhD in Mohammed's lab. So my work basically evolved around using applying diffusion model to model complex protein structure space, as well as how can we leverage those diffusion model to do specific protein design tasks, for example, motif scaffolding, binder design stuff. And so today I'm presenting my paper on Genie, which is an unconditional diffusion model for protein structure space. So, okay. So getting into that, I will start by talking about the sort of the design, de novo protein design. So I think this is a very biology group, so I don't need to mention the importance of de novo protein design. So I will kind of go straight to the two main pipeline that we are using, right? That kind of popular in the sort of design space right now. So the first one is because essentially when you consider protein, you consider its sequence, its structure, as well as functions. And in terms of design, you consider the sequence and also consider the structure. So the first popular kind of pipeline is to design the sequence and then use that generated sequence to do in silico evaluation. Basically, you running computer program to check if it's valid, and then later run it through experimental validation to check if it's actually soluble or it's actually a protein. And then the other common approach is so-called a structure-based design approach, because structure is kind of more directly related to function itself compared to sequence. So this is kind of so the second pipeline is kind of taken a lot by sort of the recent approach, including Genie, RF diffusion, as well as the recent published one, the Chroma. So basically the idea is that let's first ignore the sequence of the stuff to start with. So let's all consider the 3D structural space. Let's think about how can we model that structural space such that we are able to sample from that foldable protein structure space. And once we have that structure, the next thing is that we could design the sequence based on this structure and then go through the same process of in silico evaluation and experimental validation. And if you consider the later part of the pipeline, the structure condition sequence design, we have model for it, those inverse folding model like protein MPNN. And the challenging part here right now is the kind of the structural design part. So how do we actually model the complex protein structure space such that it's easily sampleable, and then basically we are able to generate high quality structures out of it. So that's kind of the focus or the context of this project, is basically focusing on structure design. So it's completely sequence agnostic, which is something I will talk about later, something to improve on. Okay. Yeah. So the next point I want to talk about is kind of the representation for protein backbone, because so for computer science, it's very important. It's how we actually encode things such that the computer is able to understand it as well as process information to it. And here we are considering protein backbone and how can we kind of efficiently represent the protein backbones towards a computer. So this is kind of a bit different from kind of the image space. So if you consider image space, there is just an image, it's a 2D representation, basically a 2D array. It's not as complex as a protein structure. So if you think about the backbone, what does it mean by invariant? Equivariant means that when you do a translation or do a rotation in the protein backbone, ideally we want that protein to have the same representation because it's essentially the same thing. And that's what we call 3D invariant once you do the translation or do the rotation, the representation stays the same. So that's like SE3 invariant. So here we consider like multiple common protein backbone representation. So the first one, like this is, I think the earliest work kind of dates back to like 2015 when we kind of integrate with like generative adversarial network. But yeah, previously the most common representation is the interresidual distances. Basically what we have is like you represent a protein as a distant matrix where each point kind of, where each entry in the matrix kind of trace the distance between two different residuals or two different atoms. So the strength of this representation is that it's completely free, SE3 invariant, which means that you could translate the protein, you could rotate the protein. Essentially, the representation for the protein itself stays the same because it's just the interresidual distance. Major limitation for that is that it's not reflection invariant, and this is kind of important in the biology case when you kind of consider the handiness of the protein. So that's one limitation of it. And the other is relates to sort of reconstruction error, because here you're represented it as a 2D images, as a sort of a 2D distant matrix. And once you do the generation, you generate those 2D 2D distant matrix. It doesn't guarantee that that 2D matrix is valid. It means that you can generate some distant matrix, but it doesn't guarantee that you'll be able to fold into a 3D structure. So there's an inconsistency there, and that kind of leads to a significant drop in terms of like generation quality. Next representation is sort of a torsion angle, which means that you represent as kind of the psi-phi theta along the backbone chain. This is also SE3 invariance. The issue is that sort of the reconstruction error accumulates along the chain. Means that suppose you're able to predict the torsion angle along the line, and you make a minor mistake at the beginning of it, the error kind of accumulates out, and the final structure may be completely different from what you're trying to predict, just because of the small initial error. The third representation is more kind of easy to understand. It's just Cartesian coordinate. It's just whatever coordinate, directly the coordinate of the atom. And this one, thanks to the recent development of geometric neural network like EGNN and GVP, is SE3 equivariant, which means that once you do the translation or do the rotation in the representation, the output of the coordinate will also change accordingly based on the translation and rotation. One limitation is that if you just consider coordinate or using just like graph neural network, it's not actually reflection invariant, but this one actually depends on like how you implement your graph neural network. And I want to get to the most recent one is the so-called frame representation, which makes the rigid body assumption like AlphaFold 2 made, which means that you consider each residual in the backbone as a rigid body, which is centered at a C alpha atom, and forms a frame with the N, Ca, and C atom. So that free atom actually give you a rotation metric. And here the assumption is that the bond length between the Ca and N atom and the Ca and C atom are relatively fixed. So that's the assumption there. But the good thing is that using frame representation, you are able to achieve like SE3 invariance, and also like and it's not a reflection invariant. And this last representation is like right now the most popular one or commonly used one, not just in like design, but also in like structural prediction space, like pioneered by AlphaFold 2. The last piece that I want to introduce is more like the recent development of generative model, specifically denoising diffusion probabilistic model. I'm not sure how familiar you guys with here, but I will go through a very quick introduction of this. So we have like two versions of here, but essentially they are the same. So the original one is the DDPM, the denoising diffusion probabilistic model, and the score-based model comes slightly after it, which is a more generalized version of the DDPM. So the main difference is that the DDPM is a sort of discrete time version, but the score-based model is a continuous time version. So how does diffusion model work? So the idea of diffusion model is that if you take a look at the left-hand side one, and then you start, so you start with a image. The idea is that you go through the forward process by continually destroying the information, which is your Q here, which is the so-called forward process by adding Gaussian noise. And then the reverse process will be starting from a very noisy image, you slowly kind of denoising it into the image itself. And assume that the amount of noise that you add at each step is small enough. It means that once you represent your forward process as a normal distribution, the reverse process is also can be represented as a normal distribution, a Gaussian distribution. And here is kind of one formulation of it. So essentially, when it goes down, it's like the denoiser. So basically given a noisy image, how are you able to predict the amount of noise that gets added at that specific time step? So that's the whole idea of the diffusion model, basically noising it and then denoising it to kind of do step-by-step reconstruction of the structure. Applying to the protein design space, and this is what Genie does, is having a pretty similar structure. So here what we have is that from the left, we start with a protein structure. In the forward process, we add Gaussian noise to each atom, to each C alpha atom, gradually noise it. And in here, we set a maximum time step to T. So with like sufficient noising, essentially it converts to an isotropic Gaussian distribution. And in the reverse process, what can we do is that we can sample from this isotropic Gaussian distribution, slowly run our denoiser to gradually remove part of the noise, which finally give us the structure that we have. And here for Genie, what we are only considering it is just the C alpha atom. So basically what we are learning the space is kind of the arrangement of C alpha atom. And here we kind of use an asymmetric representation here. So it means that in the forward process, we consider each C alpha atom as sort of a point cloud. And then we just add Gaussian noise into it and then denoise it into a Gaussian ball. But in the reverse process, because we need to reason about like the orientation of each C alpha atom, as well as to consider the handiness, so we're provided with more information by constructing a reference frame based on the chain of C alpha atom. So those frames are constructed using Fernet-Serrin frames to kind of inject the rotation information or frame information into the reverse process for the reasoning part of it. And yeah, so everything boils down to kind of the denoiser, which works with the reverse process, like how you actually remove noise at each time step. So this is kind of the architecture of the model. So starting with what we have is like we have the coordinate xt, and also the diffusion time step t, where here is kind of using a sinusoidal encoding of the diffusion time step. So it's named as CS. And then going through it, given the coordinate xt, we could do frame construction using Fernet-Serrin frame to from construction process to sort of construct those frame. And then the invariant encoder part here basically takes in the diffusion time step as well as the frame information, and then generates the latent representation for this structure, which output as single representation, which is kind of per residual representation, and also pair representation, which is pair of residual representation. And this representation, together with the input frame information, are used with the equivariant decoder to sort of compute the updated frame, basically update those frame, and then extract the coordinate and compute the noise vector here. I'll go through in more detail with like the arrangement of invariant encoder as well as the equivariant decoder here. So for the invariant encoder, what we have is like basically 3 components. So the single feature network basically construct the single representation, And it's very simple. It's just concatenating multiple sinusoidal encoding, including the diffusion time step, as well as the residual index encoding, which is also sinusoidal encoding. And then I don't think I used the frame here. Yeah. And then do a linear projection on it into the given dimension space. And we have the pair representation network, which combines the single representation and the frame representation into pair representation. A pair transform network using the triangular multiplicative updates module from AlphaFold 2 to basically reason and refine the pair representation. So all these are done in sort of the latent space. So basically the idea is like you've done the reasoning in the latent space, and then later you map those latent space information to update your coordinate. And that comes the next part, which is the equivariance decoder, which is the IPA module coming from the AlphaFold 2, combine multiple information, single representation, pair representation, frame information to update your single representation. And then later you use this updated single representation to later do your backbone update to compute the updated frame. So that's the whole structure of it. And once you have the updated frame, what we did is basically discarded those orientation information, because what we care about is just the C alpha atom. And then we could compute the difference, which essentially we use that as sort of the predicted noise vector. And for training, what we are following kind of the DDPM formulation from Jonathan Ho's paper. So what we have here is n represents the total number of residual. And basically what we have is just an RMSD between the noise vector there's at times that t. And you can ignore this part, is just the expansion of it based on the formulation of the forward process. But basically you're just trying to minimize the difference between the actual noise vector that gets added and the predicted noise vector, the noise vector that you predict. And if you're able to like accurately predict those noise vector, it means that you are able to accurately denoise the structure and allows the structure to chase back from a sample from the isotropic Gaussian distribution into the data structure itself, into the protein structure itself. If you have any questions, feel free to interrupt. It's like, yeah, I'm fine with it. And lastly, let me see. Yeah, so the dataset part. Yeah. So for the training dataset, we use like two dataset for training. So the first one, which is the original version of Genie, is trained on a scope dataset, which is the protein domain with classifications, and that capping it with the maximum sequence residual length of 128, because that's previously how we could fit with the GPU, but we kind of expanded later. So keeping the maximum length of 128, we have like around 4,000 structures, and keeping it at 256, we have around 7,000 structures. And the next data set that we kind of use is, sorry, the AlphaFold sweet spot data set, which give us like much more structure. So ideally in generative space, like the more structures, the better, because you have like, because you allow the model to have a better understanding of what the data distribution look like compared to kind of fewer data.
Yeqing, there's a question from Sarah about the frame representation.
Okay, yeah.
Sarah, do you want to ask that, or it's in the comments too?
Let me check it. Representation is about reduction. Okay. The vector map of the zero direction. Yeah, so basically it's
You want to clarify the question?
Sorry?
You want to clarify what the question is?
Yeah. So my understanding is that you're asking about like the frame construction process. What does the frame represent? And the other part is like, did we do noising for the frame? So I think that's, did I get a question correct?
Yes, yeah.
Okay, good. Yeah. So the first part, the construction is pretty much you could understand as that. So the first frame construction starts with like we have the C alpha atoms at the center, and then I think I took C alpha and C as the x-axis, and then you could construct using the x-axis and the C alpha and N. You're able to kind of construct the y-axis there, basically by a perpendicular angle, and then using that you could kind of construct the z vector there. So it kind of roughly represents the direction there.
But sorry, can I clarify? So that's based on your backbone atom coordinates, or the C's and N's you're referring to?
Yeah. It's based on the backbone C alpha. Sorry, yeah. Sorry,
you're okay.
Not C and N. It's just Ca atom, the adjacent Ca atom. Yeah, and the other question is it's not actually part of the noising process. So, because let me go back to the slide. So here is like for the forward process, we don't consider any frame or anything. We just consider them as point clouds, because at a noising process, it's like it's a deterministic process, or kind of. It's like we have a fixed procedure for that, and we don't actually do a lot of we don't do any reasoning for the forward process. So it's as simple as just adding noise into it. So we don't consider any frame. We just add like Gaussian noise into it. But in the reverse process, because there's like the reasoning comes from, and there we want the information to sort of be rich such that the denoiser is able to sort of reason out the structure there. That's why the frame is introduced only in the reverse process, but not in the forward process.
Got it. That makes sense. Thank you.
Okay.
Each C alpha has 3 degrees of freedom, like the X, Y, and Z, but the frame itself has an orientation to it. So is the cloud representation over the rotation of the frame? Is that, am I understanding that correctly?
Sorry, could you repeat your question there?
So there's an extra degree of freedom. Is there, I guess a question, is there an extra degree of freedom or degrees of freedom in the frame that is not captured by the C alpha, or is the constraint of like C alpha to C alpha, is the frame like rigidly oriented?
It's pretty much the frames are pretty much defined by sort of the chain of C alpha atoms, right? Because we define a chain by kind of 3 consecutive Ca atom, and once you fix the X, you fix the Y, you sort of have the Z there, so it's kind of fixed there.
Okay, so there's no extra degrees of freedom going from the C alpha to the frame representation?
No.
Okay.
Yeah.
Great.
Okay, so time. Yep. Okay. So that's kind of the architecture part of things. And now we'll move on to the kind of the evaluation part. So unlike like a lot of like predictive tasks where you have like, which is much easier to evaluate because you're able to just have a train set, validation set, and test set to kind of do the prediction, do kind of assessment there on the test set. Like for generative model, it doesn't really have that kind of luxury because you are designing new things. So to kind of assess the sort of quality of the generation, we are kind of considering, we have like multiple evaluation metric here. So the key thing here is like designability, whether the structure is actually foldable, and diversity, whether you generate the set of structure are diverse enough, means that you are kind of capturing the diverse space of protein structure space. And the last one, the F1 score is harmonic, and last one is novelty. Is like, are you able to generate like structures that are out of the data distribution? Maybe basically means that you are actually able to capture like the outside of data distribution. So I'll go through this metric one by one. So starting with the designability. So this is kind of the commonly used, like right now, the in silico evaluation pipeline for generated protein. So it's basically consists of like using 2 models, the inverse folding model and the folding model. So what we have is like, we start with the generated structure, which doesn't have the sequence. You only have like, for example, the C alpha coordinate. And then we could run that through the inverse folding model, which basically, given the structure, predict the potential sequence out of it. So for example, the protein MM model, that's what I use. So it will be able to give you a sequence out of it. And then using the protein structure prediction model, for example, ESM4, AlphaFold 2, given the sequence, we are able to predict sort of the desired structure. And kind of the score, the designability score is actually computed between to kind of check the consistency between the generated structures and the designed structures. So here the assumption is like those like structural prediction model works actually like good enough for this metric to be reliable. But because our lab is a completely like computational lab, so we don't have like any like lab resources to validate it. So I think that's like the best evaluation pipeline that we could use. So that's kind of it. So SCTM basically checks the TM score between the generated structure and the designed structure, and the SC-RMSD basically checks the RMSD between them. And the key difference here is like SCTM, the TM score kind of checks with like more global consistency. Well, if you check RMSD, it's like it's much more stringent because you need like a specific, like the two structures need to be almost the same in order for you to achieve like very high RMSD score. So here to start with like the small model, which is like our unscaled version of Genie. So what we have is like we are starting with the SCTM to be kind of consistent with like those previous models, specifically like folding diff as well as probe diff. That's like two models that comes before us. And the PRDDT basically is the confidence score that's output by the protein structure model. And this is kind of a common practice in like AlphaFold 2 as well as ESM4, Omega-4. So it kind of gives you a confidence of like the designed structure. So here the metric we're using is like CTM greater than 0.5 and a PRDDT greater than 7. And this is a very kind of loose designability metric, but we will kind of refine that later and switch it to RMSD later. But yeah, and the diversity, second metric is the diversity, which we kind of count the number of unique cluster based on TM score threshold of 0.6. So the calculation is like here we generate around 1,000 samples of various like sequence length. We're able to compute the TM score between each pair of generated structures. And then what I did is I run hierarchical clustering on it, such that each structure are clustering together based on TM score. And the last thing, the diversity is assessed by like counting how many unique cluster that we have after the hierarchical clustering. So that gives us a sense of like diversity there. F1 score is what we introduced to kind of use a harmonic mean between the designability and diversity, which gave us a single metric to kind of judge like how good those protein structure prediction model are. And last metric is the novelty metric, which kind of computes the maximum TM score with respect to the PDB dataset. So we want to check that we are able to generate structure that are actually different from the PDB dataset. So that's the last criteria.
Can I ask a question?
Yeah, go ahead.
Sorry, I'm not sure if we're supposed to raise hands in this meeting.
No, it's okay.
But I just wanted to ask, so I'm aware of PLDDT being a confidence metric like for AlphaFold predictions, but also that it correlates inversely with disorder. So I'm wondering if, considering how it's often used to assess designability, does that mean that you're also effectively excluding proteins with a significant amount of flexibility or disordered regions?
Yeah. So disorder region is kind of, yeah, it's a very kind of gray, because right now there isn't like a really good model to sort of like access those structure prediction for like this disorder region. So here what we are considering here is just like structures like, sorry, structure, yeah. So
thank you.
Yeah, so those disorder like region is actually filtered out here.
Okay, thank you very much.
Yeah, no problem. Okay. Yeah, so here are some of the initial comparison with like the some of the short models. So here what we compare is like pro-diff and folding diff. So what does it mean by short model? It means that these models are able to generate up to the length of 128. So that's like with maximum 128 residual. So we call them short model. And later there are like multiple model that's able to generate like beyond that length. And here what we have is like the pro-diff, which is using the EGNN as kind of equivariant graph neural network to do the reasoning. And the folding diff is basically is reasoning in terms of like the torsion angle space, and as well as Genie. So as we could see, like here for graph A, the x-axis is like the highest SCTM. So the higher the better. So ideally the green dotted line here, we want it to the left of the green dotted line. And the PLDT is the confidence. So we want it to be above like 70. So it's the red dotted line. So as you could see, like majority of what Genie generated structure actually fits this like designability criteria. And if we take a look at graph C, that's kind of pretty much showing the same thing. And then graph B is actually showing kind of the secondary diversity, the distribution of it. You can see that Genie is like much more diverse in terms of like the secondary structure diversity compared to like folding diff. And graph D is showing like kind of the number between like designable, which is just SCTM greater than 0.5, confidently designable, SCTM greater than 0.5, and PLDT greater than 70, as well as novel and confidently designable. So as you can see, like Genie is able to generate like substantial amounts of like, not substantial, it's like I think this is like 10%, something like that, of structures that are actually like considered as novel, which is not that bad consider like the complex protein structure space. And the next part is like we move, because so these are short model. So the next part of us is like we move on to compare with like long model, which is basically frame diff and RF diffusion, which are capable of generating structures much larger like structures with maximum sequence length beyond 128. So here for like consistency of comparison, we keep everything like at max of like 256, which I think is pretty large enough at least at the point of assessment. And then here we kind of show everything in a table. So here for designability is not considering SCTM, but it's considering SE-RMSD less than 2, which is consistent with like the evaluation metric in R diffusion. So it's a much more stringent criteria, because it's kind of enforcing that the structure that you generate must be within like 2 angstrom of the actually designed structure. So it's much more stringent criteria. Diversity is the same. Assessments of like number of unique cluster, F1 score, and novelty are the same here. So as we could see here, it's like Genie is like performing better than frame diff in terms of like, exploring frame diffs better than frame diff in terms of like designability, diversity, and F1 score, as well as novelty. And an interesting thing here is like the number of like parameter that Genie use is like much smaller compared to frame diff. And if you consider like Genie scope, compare Genie scope with frame diff, is like the amount of training data set that we use is also smaller than frame diff for Genie scope. However, the performance is also better than frame diff. So that's one key takeaway from it. And then the other thing is like our diffusion still outperform us significantly in the sort of the designability range. If you're considering the RF diffusion with like Genie switch process, like it's like 15% better than Genie in terms of designability. However, there are several caveats to that. Like first of all, it's like RF diffusion is much larger. Second is like RF diffusion is using pre-trained Rosetta fold model to start with, which means that it's seeing much more data, because Rosetta Fold is like trained not just on PDB data set, it's also using some of the AlphaFold database. So it's like seeing much more data, and then it takes more time to train. So there's two caveats on that. And then right now what we are doing, we also like scaling up Genie, and to kind of get some better assessments and better comparison between RF diffusion and Genie. And the last part is the sampling time, which I just report a number here, but I don't really like I haven't optimized them yet. So you could see like for our fusion, it runs like 50 sampling step, which takes around like 0.74 seconds. For us, we take like 1,000 sampling step, because I keep it as the same as the kind of number of diffusion step. It takes like 1.3 seconds, and the ratio here is like different. It's like once we optimize it, we should be able to like achieve like faster sampling time. But yeah, this is something I'm working on right now. I haven't like I haven't fixed this part.
So before we move on, for the novelty, this is novel relative to what data set?
PDB data set.
And what as far as the training data goes, was the RF diffusion and the Swiss prot set, or the scope set that you had, consistent? And like were those PDB structures in the training set for both of these models?
Yeah, so it's like different stories. So so if you check the novelty part, like for Genie, the scope is like pretty much within the PDB data set. And for Genie, the AlphaFold DB Swiss prot, I haven't checked the overlap of it, but there are definitely some overlap with the PDB data set there. And then for RF diffusion, it's like a totally different story. So RF diffusion itself is like trained on PDB dataset. It's trained on PDB dataset itself. However, it's kind of using pre-trained weight for Rosetta Fold. And Rosetta Fold is like trained on not just PDB dataset, it's trained on also AlphaFold database. So it's kind of hard to access the scale of training dataset here.
So these novelty scores should be taken like with a little bit of caveats in terms of novelty relative to maybe not necessarily the same training data sets for each model.
Yeah, correct. That's the small caveat. And then in some of our version, what we are running is like we are comparing, because the idea of like novelty is sort of like relatively. So this novelty reported here is like relative to the PDB data set. However, we are also computing kind of the novelty with respect to the whole AlphaFold database, which is kind of consistent with like some of the recent version of Genie, and we are also like seeing much higher novelty compared to RF diffusion. Yeah.
And I guess, how do you rationalize the fact that diversity and novelty are not always correlated or anti-correlated? Are you sort of sampling in these fixed sort of spots in protein space versus like kind of spreading out into non-protein space? I guess, how do you think about this?
Yeah, so generally like diversity and kind of designability are actually like correlated. It's a higher designability sometimes usually leads to like lower diversity. But a lot of time, like if you consider like model architecture, sometimes some model are actually better to capture like different parts of the protein structure space. And what it means that is that you are able to see like higher designability and diversity at the same time. So in some sense, what I was reasoning about like frame diff and Genie scope is probably some of like architecture edge there. It's probably that's like allow us to better capture like different region with like higher accuracy, or higher accuracy basically.
I have a very sorry, go ahead.
No.
Sorry, I just have a very generic question. Do novelty and diversity of things generated by a diffusion model go down the longer you train it, or is it just that those stay the same and quality improves?
So from what I observe is like as you train longer, usually designability goes up, diversity kind of goes down. And then I haven't checked the novelty part across time because it's much costly to run those like novelty assessment because you kind of compare to the whole data set. But that's kind of the general trend there. But
Okay,
kind of
so
the extent of like drop in diversity also like vary across like different model architecture, etc.
So is there a trade-off in deciding when to stop the training between designability and diversity/novelty?
We just run it for like 10 epochs, 20 epochs, and just stop it at that point. And then kind of access sort of like some of the intermediate models there and then kind of make a decision there. We didn't really like kind of find the optimal point there.
Okay,
Yeah,
thank you.
no problem. Yep. And last part, this one is just yeah, pretty much done. Yeah. So last part is the visualization of the latent space. So on the right, we are showing kind of the maximum theorem score relative to like the PDB structure. We are seeing like pretty much like diversity across the space. And on the left, we are seeing kind of the distribution of like helixes, strand, and length as well. So it's kind of and it's also showing some of the example there. So the key takeaway from this, I think, is like we are able to sort of generate like novel structures sort of across the space with with different like secondary structures.
So all of these have very low radius of gyration, like they're all very round. Do you get like in terms of the natural distribution of proteins, like in the protein data bank, are you able to get like elongated structures that have, that are not as compact?
I haven't verified that. Yeah, this is something that I haven't verified. Yeah.
As a comparison point to RF diffusion, I mean, I would consider this a failure state of RF diffusion, but you can definitely get it to give you elongated structures. Even as far back as the first Rosetta fold, it had a failure state of, I know what a helix is. This whole protein's one long helix. And that, like, it's almost genetic in the heritage of that software stack. It does still have that failure mode lurking in it. It may be a truth mode too, but it's available as a failure mode to give you extended proteins.
There was a really nice work from the OpenFold where they saw that over time, the emergence of like being able to get different secondary structure or different folds sort of emerged over training. So like helices came first and then beta sheets and then sort of other topologies sort of emerged over time. I'm curious if with more training, you'd be able to get sort of more diversity of structures.
Yeah. That's a possibility. We're kind of scaling the model right now to have sort of a better understanding on that.
Hey, can I ask why the percent beta sheet is so low? Not just in this model, but I think Chroma also had trouble with beta sheets, and I don't know about RF diffusion. But those proteins that were made certainly seemed very helical to me. So I was just curious what your thoughts were on why the topologies you're generating are at most 30% beta strand.
Yeah. So there are like a couple of, at least some of my hypotheses to that. So first of all, it might have to do with like the training data set. So if you think about like the training data set, the kind of percentage of helixes is usually more than a percentage of strand. Like if you consider PDB structures, because I don't think I showed the diagrams there. Yeah. But yeah, so first of all, it's like kind of the distribution in the data set that kind of has an impact on that. And the second part is, this is my hypothesis, I'm not sure it's true. So inherently, it seems like there are much more diversity with those helical structures compared to like beta stranded structures, and the model seems to devote more resources towards like learning those helical arrangement or helical beta arrangement compared to like learning those with like mainly beta sheets. So that's another hypothesis there. Yeah,
they also have a much higher contact order, like the interdistance between residue contacts is much higher for beta sheet structures.
Sorry, could you repeat that?
Like if you have strands that are coming together, like I don't know, I know that the distance between interacting residues has to go all the way up and back, whereas for a helix, it's very close. So there's the structure is sort of more locally organized into the.
Yeah, but yeah, that kind of goes to like sort of long range interaction.
Mhm.
I think that's what you're talking about. But I think it shouldn't be an issue for like Genie or this kind of like IPA architecture, because it's basically using full graph to do the reasoning.
Okay.
So it shouldn't. Yeah, I don't think it's an issue with like local arrangement or long range interaction there.
Fascinating.
Yeah. Does that address your question? Okay. Yeah, and the last part is some of the next step that we're running with is like, first of all, is like conditional sampling. Like given this like, unconditional model, how well are we able to like use it for like motif scaffolding? And yeah, it's interesting to see some of the recent paper they are using Genie to do like motif scaffolding also. So it's pretty good. And next one is the integration of like sequence information, because yeah, as I mentioned before, is that all this diffusion model actually like sequence agnostic, but a lot of times sequence information would actually help a lot, and it's kind of an important part, especially when you're kind of trying to design like sequence motif, etc. So that's kind of one step that we are kind of doing right now, is like how do we integrate sequence information, and also at the same time, like how can we actually extend not just backbone atom, but also extend it to the sort of full atom range. And the last part is like scaling performance as well as like complex modeling. That's kind of what we are interested in right now. So, and some of the next step that we are doing right now. Yep. So I think that's all my content. So
Hey,
thank you everyone for listening. And then I want to thank my advisor, my PI, Mohammed. So
All right, let's thank Yeqing. And questions.
I have a question
Yes,
about
please.
the time step embedding. Is
Yeah.
there a reason why you chose to do sinusoidal embedding rather than just like a 0 to 1 like scale?
No, it's yeah, I kind of consider it as kind of similar to positional encoding, and then you run it through like sinusoidal encoding, it sort of provide like a much higher dimension, like richer information in some sense, compared to like just a single number there. But yeah, you could change to like different forms of encoding. But yeah.
Thank you.
No problem.
More questions? So I guess one of the things that we've been seeing is the design space in terms of the representation and the encoders and decoders and different noise schedules. It's really fun to see exploring different parts of it. And I'm curious if you could, based on your experience, if you have any thoughts on like what are the sort of the key ideas that you think are worth implementing in other models versus ones that you've now seen that you think are superior or, you know, or somehow make different trade-offs than the ones that you've done.
Sorry, could you rephrase your question?
So like, for instance, you use the IPA, which I think is somewhat unique in terms of in these diffusion models. Is that a good choice that other models should do too? Or is that like with the n cubed complexity, you know, it's not worth the computational cost of it?
Yeah. Okay, so yeah, with regards to like multiple components I'm using is that, for example, triangular multiplicative updates as well as like IPA. I think they are like pretty nice module to use. And at least like from some of the experiments I have, it's like IPA is like it's showing like better performance compared to like previously like EGNN, like equivariant graph neural network. Some of those, at least that's from my own experience. So I think those are like very, very good, very nice module to use. And yeah, the time complexity part is another issue. It's like it's taking n cube, and but that's kind of the trade-off between like performance and running time. So I think that depends on like the use case. Is like how large the model, how large the protein you want to model, and like how much accurate you want it to be. So yeah.
And I guess in terms of the designability versus diversity, I'm curious on like there's a supplemental figure on the noise schedule or the sampling noise scale. And I'm curious on if that's a knob to twist in terms of like if there's a sweet spot in terms of the F1 score and how like it looks like as you go up, like the F1 goes up, but then as you go too far, you kind of are off that balance. I'm curious on sort of, is this an inherent part of the network? Is this because it's a small, it's relatively small, or is there other sort of ways to stabilize it? Like what's going on here?
Okay, so yeah, so the sampling noise scale kind of, I think it's introduced, like at least in the protein design space, is like first introduced by Chroma, so it's similar to kind of the low temperature sampling stuff. So basically, like it kind of basically controls the amount of noise that gets re-injected in the sampling process. So the higher the noise that get re-injected in, you are able to achieve like higher diversity. But because you are adding more noise to it, the model is not kind of really able to figure out like what's the designable structure out of it. So your designability actually goes lower. However, if you decrease the noise scale, it means that the model is able to kind of gradually refines them, is able to achieve like higher diversity because but without the noise injected, it's not able to achieve like very high diversity. So so for practical standpoints, what I did is I usually just run it across like a grid scale between like 0 and 1, and then see which one actually performs better. And the goal is like there's like a sweet spot somewhere between like 0.6, where you kind of find sort of a balance between like the model designability and the diversity. However, the noise scale actually like varies with like different model. Like sometimes when you train the model longer, the designability goes up, which means that you are able to kind of use higher noise scale, but without sacrificing too much with the designability. So the noise scale is a very tricky part. So it depends on like it depends on multiple factors, the model architecture, the sort of like the training time of your model. So and yeah, a couple of things.
Great. Any other questions?
How long did you have to train each version of your model? How long did it take?
So right now I have a comparable one, and then it I think it's around 5 days on 8 V6000 GPU.
Okay, and like
Yes.
what's the amount of time per epoch?
I run it for like 10 epochs, so it's like 12 hours, something like that.
Okay.
Yeah. But it depends on the data set that you're using.
Yeah,
so
yeah.
if a large data set, you take a longer time.
Okay, thank you.
Yeah.
Any other questions?
And can I ask one more?
Yeah.
So I saw in your table that was showing the different numbers of parameters that, I mean, Genie gets this performance with so few compared to these other models. What is it about Genie that makes it able to accomplish this task with so many fewer parameters?
My guess is like with the use of IPA and triangular multiplicative updates, which kind of do the sort of refinement of the pair representation, which allows us to use like less model. Somewhere like the architecture is more efficient, that's my guess. But yeah, that's only my intuition. I don't have like any result to actually substantiate it.
Okay, thank you so much. This is a nice paper.
Yeah, no problem. Thank you.
Any other questions? Okay, I have one. So in your assessment of designability, you're using OpenFold, is that right? Or is it AlphaFold too?
I'm using ESM fold.
ESM fold. And
Yeah,
I'm curious on if you have any thoughts on whether or not that's introducing bias. I guess it's hard to tell without experiments, but in your assessment, are there, maybe from playing with this enough, you've recognized that ESM fold like certain structures more, or that there's certain sort of aspects to the assessment that maybe is not as fair as it could be, given that there's sort of this model-based assessment?
I didn't look into like much detail. I just run the pipeline and check that the structure looks reasonable to me. I didn't look into like detail, but I actually I did some kind of comparison, like switching with different model, like switching with Omega fold, and I think I switched with AF2 sometime. But it's the performance kind of vary a little bit, but it's pretty much consistent. It's like something it says designable is pretty much designable like across like pretty much all the models there.
That's good to hear.
Yeah. But yeah, ultimately this depends on like how good do you believe in those like putting structure prediction model. Yeah.
Can I ask a general question dovetailing off of that?
Yeah.
So you say that the performance varies to some degree between the different models used in evaluating it.
Yeah.
And I'm wondering to what degree is that because, like, for instance, AlphaFold, needs to build an MSA, and if you're generating sufficiently novel sequences, it may have some difficulty doing so.
It's hard to say. I think that's kind of a contributing factor, like using like a language model and MSA. There's kind of one possible reason for that. And then because like the sort of like 3D reasoning of ESM4, yeah, it's pretty much similar. Yeah. But the other thing I want to say is like probably the reasoning architecture is another like potential reason out of it. So it's hard to say. It's like those are huge model, and it's hard to like segment them out and then compare them piece by piece. So
Okay, thank you.
yeah, no problem.
Okay, well, let's thank Yeqing one more time.
Yeah, thank you very much everyone for listening and having me here. It's my pleasure.
Okay, and we'll try to be back in 2 weeks. Actually, that might be close to Christmas. Well, anyway, watch for announcements and we'll figure out when the next time we're meeting. So see you all soon.
Bye.